This is Lecture 9C for Calculus 2 on methods of solution for differential equations. So in this lecture, we're going to look at some methods for solving certain differential equations. The differential equations we're going to solve by this method occur very, very frequently in all disciplines, so these are very important tools to learn. The first is the method of separable equations. It only applies to equations that are separable, and we'll see how that works in a minute. Then there's the use of the integrating factor. The integrating factor can be used to solve first-order linear ordinary differential equations. Those are our two analytic methods. Then there's a numerical method called Euler's method. And then there's a way to extend from first order to higher order differential equations under certain circumstances, so that we can use these methods, these analytic methods, to solve second order differential equations, because we can rewrite them as first order linear or first order separable equations. We're going to start with the method of separable equations. So we have to define what a separable equation is. This is a first order. That means the highest derivative is the first derivative. It's linear. Everything's to the first power. The derivatives and the function are to the first power. And it can be nonlinear, in which that doesn't hold. Ordinary differential equation, meaning there's only one independent variable. So it is a separable equation of these categories that can be written in the following form. Here is your first order, so here's your first derivative. You can write it so that there is some function I'll call n of y that multiplies the first derivative after the equal sign function are all functions of x. This can just be a simple constant like 1, but we have to be able to write it in this form. So m contains all terms that vary with x. N contains all terms that vary with y. You could isolate dy by dx, then you have dy by dx equals all the terms that vary with x divided by all the terms that vary with y. Here are examples of separable equations. Dy by dx equals x squared over y. In the numerator, the terms is x squared. It varies only with x. In the denominator, we have y, which again varies only with y, or rather not with x. We can write this in the standard form. Y is here. Dy by dx equals n squared. I'm going to write that form above so we can remember what it is. We have some function which I'm calling, let me get the pen instead of the mouse. Go. N of y times this first derivative, dy by dx, equals some function of x only. So here our n of y is y, right? And the function m of x is just x squared. Here's another example. Dy by dx equals x times e to the y. All right? We can write this in standard form by multiplying both sides by e to the minus y. So here is my n of y, which is a function only of y, multiplying the first derivative on the left-hand side. On the right-hand side is a function only of x. In this case, it's just the function x. In this next example, let me get rid of some of that writing. In the next example, dy by dx equals 5 times 2 plus y. Right. We can write this in standard form if we divide both sides by 2 plus y. So in this case, we have 1 over 2 plus y. That's the function n of y. It appears down here. Dy by dx equals, and in this case it's 5. M of x equals 5, just a constant, and that's perfectly acceptable. Right. So those were some examples. And I'm going to write again what we started with, and that was some function of y multiplies the derivative dy by dx equals some function m of x. Okay, we can rearrange. So I have ny dy equals mx dx. Then We're going to integrate both sides. These are indefinite integrals. Once you have done this integration, you are done with the calculus part of finding the solution. After this, you only need to use algebra to isolate the independent variable, or rather the dependent variable.